Hello and welcome back. We're moving on in equation writing and we're going to focus in on this part 2 video on combustion reactions and single replacement reactions. My students' combustion reactions might show up on a different spot in your note packet, so just flip to it, find it, and then we'll go back and do our single replacement reactions afterwards. So you know from the summer assignment that combustion reactions are made up of a hydrocarbon reacting with oxygen gas to make carbon dioxide and water. You can also have an oxygenated hydrocarbon, which would have oxygen involved, but in general, you're going to see these as our hydrocarbons. Now, we don't do a defined organic chem unit in our AP chemistry until after the AP exam, so you're going to see a little bit of some organic chemistry sprinkled in throughout the year because it's important to be aware of some of the compounds that we'll be dealing with in various reactions that we deal with on the exam. So one little thing is, and this is in the Regents reference tables, but just so you can have an idea of where this is coming from, if we, in letter A, had to write a reaction for the combustion of ethane gas, ethane, we can actually use our tables on here to get the formula. So our organic compounds actually have a special set of prefixes that represent the number of carbons. And for ethane, eth would be 2 carbons. And then ethane, we'll see up here based on our examples. Ethane is an alkane, which means it follows this general formula. So we would have C2, and then H would be 2N plus 2. So 2 times 2 is 4, plus 2 is 6. Okay, you don't have to memorize this at all for AP chemistry right now. We have the tables when we actually get to it at the end of the year, but just so you are kind of being cued in on some of this stuff. So then we're going to actually undergo the combustion reaction here. We're going to have C2H6, and for our hydrocarbons, anything with carbons 1 through 4 are going to usually exist as gases at standard conditions. Anything 5 carbons or higher, as in terms of our hydrocarbons, like our alkanes, are going to be liquids. So for ethane, we're going to put this in as a gas. It is always going to react with oxygen gas. It is going to produce CO2 gas, carbon dioxide, and water vapor. Okay, and then from there, it's really just balancing. Let me just go through one, and then the next one I'll have you pause and I'll just show you the answer. But if you were to do this and say, just balance, the carbons and hydrogens first, and you're gonna see me making some scribbles in a second, so if that bugs you, do pencil. So you have 2 carbons and 2 carbons. I have 6 hydrogens here, and I have 6 hydrogens over here. The problem is when I add up my oxygens over on this side, I have 4 plus 3. I have 7 oxygens. Well, there's no whole number that I can multiply by 2 to get to 7. So if we try out having our 2 ethanes, I now would balance that out where I have 2 times 2. I have 4 carbons. I have 2 times 6, which gives me 12 total hydrogens. So 2 times this coefficient 6 would balance that out. Now if I check my oxygens, 4 times 2 is 8. 6 times 1 is 6. So that gives me 14 oxygens, okay? So if I go to balance out my oxygens on my reactant side, 2 times 7 will give me the 14, okay? So usually for students' combustion reactions, it's just the balancing part you might have to take a little extra time with. So for letter B, we're gonna do liquid hexane. So hexane would be C6H, and then 2 times 6 is 12, plus 2 is 14. And then we can go ahead and write out this one. This is liquid. And then again, O2 is always a product, and then our carbon dioxide and water are going to be O2 is always a reactant. CO2 and water are going to always be our products in a combustion reaction. So pause the video and see if you can actually balance this out on your own. Okay, hopefully you tried it out. And if you did try it out, you should get these coefficients. A 2 in front of our hexane. We're going to have 19 oxygen molecules. We're going to have 12 carbon dioxides and 14 waters. Okay, we're going to be coming back to combustion in a week or two, so make sure you feel comfortable with at least that part of it. All right, so now we're going to kind of jump back and look at our single replacement reactions. If you remember from the summer assignment, in this case, with a single replacement reaction, you can think of it as you have an element and a compound. Okay, an element's going to come in and kick out one of the components of the compound, so that in this case, B would be by itself, and then now A has been bonded to C. So where we need to go now is writing out in predicting the products of a single replacement reaction. Now, not all single replacement reactions will occur as written, and part of this has to do with the activity of various metals and nonmetals. Now, in our Regents reference tables, we have this great tool called Table J, which helps us determine and make these predictions, which you're not going to have for the AP exam, but you'll start to see some general trends, which will make a little bit more sense throughout the year. You'll see a lot of the group 1 and group 2 elements up at the top. You'll see some transition metals and so forth as you move down. So just kind of be aware of their general order. And we'll talk about this as we kind of go. So here we're going to write a single replacement reaction for solid magnesium and aqueous tin 2 chloride. In our single replacement reactions, almost always the compound is going to be aqueous, which will be important. So here I'm going to have magnesium, which is our solid, and then tin 2 chloride. Tin is going to be +2, chlorine is -1. So this is going to be SnCl2, aqueous. Okay. One thing we would check for is to make sure on table J, I have Mg up here, I have tin below. The element that's by itself that is going to do the replacing, that has to be higher than the element that's in the compound that it is going to replace. If it is not, the reaction will not occur. So for this, because magnesium is higher than tin, it's going to come in, you don't actually have to draw these arrows, and kick out tin, which means tin is going to be by itself. It's monoatomic. It's a solid at STP. And now we're going to have magnesium bonding with chlorine. And I always tell students, whenever you write a new compound down, always check charges. So Mg is +2, chlorine is -1. So that formula is going to be MgCl2. This being Cl2 does not have to do with the fact that there was 2 chlorines on my reactant side. This is because I'm balancing these charges within this particular compound. And then your product compound here will be aqueous, meaning remember that it's just mixed with water. Okay, so that's our first example. Let me just point out to you, if I had had this reaction to start, where tin was going to try to undergo a single replacement reaction with MgCl2, that actually would not occur. That would be no reaction because of the fact that tin is not more reactive than magnesium. So that's where table J comes in. All right, let's try out these other two. With B, we're going to be undergoing a single replacement reaction involving our nonmetal components. So we have chlorine gas, and then we have aluminum bromide. So Al is +3, bromine is -1, so that's going to be AlBr3. And this would be, a solid in this case, which is a little bit different. It has to do with the nonmetals. I should have mentioned that in letter A. So in this one, the chlorine can't replace aluminum. It has to do with charges, a few other things. So chlorine being a nonmetal is going to replace the nonmetal within the compound. So if we double check on table J, chlorine is above Br, so this reaction can occur. So chlorine is going to come and kick out bromine. This is where you have to be careful and really know that information from part 1. Bromine is a diatomic, so it's going to be Br2. Bromine is also a liquid at STP. And then you're going to have aluminum bonding with chlorine. Al is +3, chlorine is -1, so you would have a 3 here. And then that would also be a solid state. Okay. Then it's just a matter of balancing. Don't forget to check that at the end. So in this case, we're going to need to make 6 chlorine, or have 6 chlorine on each side. That also, I put a 3 here. That should be a 2. Okay, if I balance out the bromines, this needs a 2, this needs a 3, and then that also balances out the aluminum. So that would be your final complete equation there. Okay, our last reaction, which is a little bit different than in your packet, I just wanted to make a change because it's going to be more similar to what you're going to see in class. We're going to do a single replacement reaction between solid zinc and then our aqueous lead-4 nitrate. So in this one, and zinc is higher than lead on table J, so this reaction can occur. We're going to have solid zinc, and then I'm going to write Pb, which has a +4 nitrate. Our polyatomic ion has a -1. So that means I'm going to need 4 of our nitrates there. And then this is going to be aqueous. So when we go to write the product, zinc is going to replace lead in the compound. So now we're going to have Pb solid by itself. And then zinc is going to be an element that has a +2 charge always. It's one of those exceptions within the transition metals section of the periodic table. So like I said, our new compound has to be based on their charges. So zinc is +2 and nitrate is -1. So in this formula, I just need the 2 nitrates, and then that will remain or be aqueous. And then obviously we have to balance it out. So I'm going to need a 2 to get my two, not there. We're going to need a 2 down here in front of our zinc nitrate in order to get our 4 nitrates, and then that will cause me to put a 2 in front of zinc. So we will keep practicing these tomorrow, but I wanted you to get an overview of what we're going to be doing.